Hi, my name is Ingo Müller, and today I'm going to present the collection virtual machine, an abstraction that we've designed for multi-frontend, multi-backend data analysis. We are thinking of collection virtual machine as being for collection-oriented data analytics, what LLVM is for low-level compilation, a single compiler infrastructure that allows to run multiple front-end languages on many different target backends. The problem that CVM is trying to solve at the core is well known in this community. For decades, we are porting SQL to whatever new architectures are coming up. However, since a few years, this problem is becoming more and more complicated as people are trying to run more and more different styles of analytics. And the tools that exist today are not ideal. Take a system like Spark, which runs basically any type of analytics, but only on large scale clusters. When run on different targets, its efficiency is quite suboptimal. TensorFlow may be more efficient in the things that it targets, but it only targets a subset of it. And SQL can run on any architecture efficiently, but can really only do SQL. And quite frankly, most of the tools that are used in practice today are just single core, and they specialize for one of the types of analytics. So what I want to illustrate with this is that today there is a plethora of systems and none of them covers them all. And this illustration is really just a simplification. The real world looks more like this. Now, there are some obvious problems with that. One is for the users who, when they switch their target architecture, they need to switch their tools and re-implement everything that they did. Similarly, if we try to combine different styles of analytics, they are most often forced to copy data around and integrate such that the different tools work together. And for us, maybe most interestingly, is that we are re-implementing the same components over and over again for each new front-end, back-end combinations that we want to support. And now there have been some attempts to overcome this situation. Relational algebra for SQL is probably the most prominent example. But people have also tried to target different types of analytics. For example, linear algebra and relational algebra in the same engine, graph analytics and relational algebra in the same engine, vectorized execution on many platforms in the same engine, or basically any type of analytics on single core or single core to multi-machine systems. However, all of these are really great efforts, and we absolutely want to build on them rather than to replace them. However, all of them made some choice, and none of them really covers all of the front ends and all of the back ends. And the fundamental reason, as we believe, is how these systems are built, in a way their development process. The problem is the following. What most of these systems do boils down to the following. They choose some front-end, back-end combinations with potentially several front ends or several back ends. They identify common concepts between these front ends and back ends, and then implement the system from scratch, potentially looking at literature to get inspiration on a conceptual level. The problem is when they want to target another front end and or back end combination, they start completely over and repeat this entire process. And the problem is that this doesn't seem to scale to all front ends and all of the back ends. So we want to improve on that. And now our core idea is the following. We want to build a common infrastructure that we only need to build once. And from that point on, whenever we choose a new front-end or back-end, we can identify common components that have already been implemented in that infrastructure and reuse those that fits. Importantly, we're talking here about components and not concepts. We might need to add new components that are specific to the new front end or back end that we're adding, and we might need to refactor some of the existing components based on the new experience from that that implementation process. And then, importantly, whenever we want to add another front-end or back-end, we don't start from scratch. We reuse the entire infrastructure and potentially the components that other front-ends or back-ends have already used. Now, what we need for that is that common infrastructure, and that is what we have done so far. This is basically what CVM and this talk are about. The big question that we need to answer for this work is what really is the smallest common denominator. And we believe that the compiler infrastructure for intermediate representation is the key answer. The overall architecture looks as follows. The different frontends are really just frontends that are thin translation to some intermediate representation that is very close to the specific frontends. And then there are rewriting passes that first bring them into some more common intermediate representation, and then a more target-specific or backend-specific intermediate representation, which can eventually be lowered into executable form that is specific to the particular backend that the user has decided to use. There are one key distinction between existing approaches that have used intermediate representation is that we only define an IR language rather than one specific and fixed IR. And in this IR language, the goal is to make it really easy to define concrete IRs and hence to evolve them, to add new ones, and even to combine different existing ones. And since all of the IRs use the same framework, we can not only reuse the tooling around the IR, but also some of the IRs themselves and the rewriting passes defined based on them. Now I need to. The IR language really allows to define two things, and the first thing that I want to describe here are collection data types, or more precisely collection types. So I'll do that by example. In fact, all of the types of analytics that we are targeting are based on some type of collections. For example, relations, which may contain structs and arrays, graphs, which really consists of vertices and edges, and linear algebra, which is defined on tensors. And what all of these have in common is that they are some form of collection of items, where an item may either be an atom, a tuple again of items, or a collection again of items. So we have this recursive structure that all of the types that we ever need can adhere to. What is really important is that we can, inside this type system, we can add new atomic types as well as new collection types. And this allows us to define the examples that we've seen so far. For example, we can define the type bag in order to represent relations as bag of tuples with identifiers, which may potentially be nested. We can define graphs as bag of vertex identifiers and pairs thereof for the edges, as well as tensors as sequences, or which may be as potentially nested sequences of numeric atoms. And now I've shown you here how high level or application level collection types could be modeled. The same is true for very low level collection types that correspond to how execution engines may work. For example, we can define a type vector for a single allocation or C array and a tuple for a C struct. And just by defining those two, we can already cover a huge number of application techniques that are typically used in this community. For example, we can define a row store as a vector of tuples, a column store as a tuple of vectors, dense linear algebra as vectors of floats, and sparse linear algebra as nested vector of column ID value pairs. If those are not enough, we can. It's very easy to define new types. For example, if we have a particular hash table that works well for a particular application or platform, we can define a new hash table type and extend the available types with that mechanism. Now, what is important here is that in the CVIM-IR language, we only define the structure of types and not a fixed list of them, such that it's easy to add new types or evolve the existing ones. Similarly, we also define the structure of instructions or operators, and we do that as generic as possible. They have an arbitrary number of inputs, an arbitrary number of outputs, and they can be parameterized again with an arbitrary number of parameters, which may be again which may be functions or again programs. Let me explain that with a couple of examples. For example, we can define the typical relational algebra operators, which will all have a single output as follows. For example, the join has two inputs, one output, and a condition as a parameter. The projection has the projected attributes as parameter, and the selection as a predicate as parameter. We can do the same for MapReduce and Spark-like frontends, where we represent the higher order functions as instructions that can be parameterized by a first order function. And finally, we can even define operators for control flow like structures. Here we see a loop operator where the loop body is represented as a nested program or nested query plan that is given as a parameter to the loop operator. And again, we see here high-level instructions that are close to what an application might want to do. The same concept also works for physical operators. If at some point the compilation chain has decided to run some repartition operator, we can split that up into very physical, very fine-grained operators, such as a partitioning operator on both sides, and then a build and a probe operator that are run jointly on each of the partition pairs. This allows us to represent very low-level, very fine-granular execution details in our IR. The benefit of doing something like this is that if we have a similar join that is application-specific, for example, for graph or spatial joins, then we can reuse a large part of that, a large part of the components. In this example, the partitioning and the joint execution on partition pairs. And what is important here is that we only define in CVM the structure of operators and not a fixed list of them, such that whatever we might need to add in the future, we can do that in that IR language. Now, what we've done so far is implement 3 different IR flavors for 3 different target platforms. We have implemented Modularis, which targets RDMA, which targets RDMA clusters, Lambada, a system that targets serverless cloud infrastructure, and JITQ, a system for single core in-memory execution. All of the 3 systems share a common frontend that is based on a Python interface for generic data flow computations, which translates the user program into an initial intermediate representation. Then there's a number of rewriting passes, much of which are shared across the 3 systems, but some of which specialize the program for the target platform. And then there's a number of executable components, again, many of which are shared across the 3 systems. But for example, the cloud system has some specific execution components that are specific to that setup. Let me now very briefly present how this works in terms of performance. We compare JITQ, the single core system, with other in-memory, state-of-the-art in-memory systems. For example, here on TBCH, we achieve a similar or at least not too much worse performance than systems like Hyper and Flare. And for k-means, we achieve the same speed or even slightly better than the handwritten and hand-tuned implementation in scikit-learn. For the RDMA cluster, for the RDMA backend, Modularis, we compared with two systems, memSQL that keeps the data in memory and Presto that reads it from distributed storage. In the latter case, we are able to outperform the existing system Presto by about an order of magnitude, whereas with memSQL, we are at least in a similar ballpark or not too much worse. And finally, the system for serverless functions, which by the way I will present in more detail tomorrow in Sigmod, which is called Lambada. We compared with two commercial serverless SQL analytics systems, and compared with Athena, we are often about an order of magnitude faster, or at least, sorry about that, or at least significantly faster, while at the same time being between 1 and 2 orders of magnitude cheaper. Compared with BigQuery, we are not quite as fast, but never more than 2 to 3 times slower, and at the same time being at least 1 and often 2 orders of magnitude cheaper. On all of these three platforms, our CVM-based system is usually on par, is roughly on par with the best-in-class system, and often significantly faster. In order to summarize this work in CVM, we have defined an IR language and a compiler framework around that is meant to be a timeless core for different frontends and backends for data analytics. And having this timeless core makes it easy to extend, combine, and evolve concrete intermediate representations that are specific, that to some degree may be specific to the to specific frontends or backends. The current three platforms that we've implemented provide an initial validation, but of course there's more work to do to show the full breadth. That's what we want to do in the near future. With Modularis, we have started building modular execution layers and concrete IRs that expose that to CVM. We haven't quite covered all frontends and backends yet, but already quite a large number. And as time passes, we hope to add more. One of the frontends that we are particularly interested in is to add streams to the picture, and we believe that we can model streams as infinite collections and use the CVM IR language without modification for that type of collections. And once the concrete IRs have stabilized a bit more, or in parallel to the IRs, we also need to extend, optimize, and compiler technologies, which we believe might be challenging for such a large number, or for that potentially large number of collections of instructions and types that we are targeting. And with that, I'm done with my talk, and I'd be happy to answer your questions.